Good morning, class. Today we're going to talk about a new abstract data type called the tree. Okay. Unlike one moment. Unlike lists, stacks, and queues, trees are considered non-linear data structures or ADTs. And once again, I repeat, what is linear ADT? Basically, there is sequential organization of data. And non-linear means there's no sequential organization. Trees have a special type of organization, unlike the hash tables. Hash tables are also non-linear data structures. This is called a hierarchical organization of data. And we'll see why. This is extremely useful. There are many, many applications of trees. And let's start with a simple example of a tree. I'm just going to take some nodes. Let's say this is 1. And this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. Special type of trees are the binary trees which have only two branches. This is a special node which is designated at the root, and it's called the root. And the root node has children. These are all children of the root node. And these children of the root node are these are called 2, 3, and 4 are siblings, and 2, 3, and 4 are also children of 1. And 5 and 6 are children of 2, and 5 and 6 are also grandchildren of 1. Okay. And so on. You can keep, so basically there is a nice hierarchical relationship between the nodes. In much the same way we say that 2 is a parent of 5 and 6. Just like we have the grandchild relationship, we can also say that 1 is the grandparent of 5 and 6. Now notice that 5, 6 do not have, 7, 8, 9, 10 don't have any children. So 5, 6, 7, 8, 9, 10 are called leaf nodes. While all other nodes which have children are called internal nodes, including the root, because it has children. So 1, 2 in this example, 3 and 4 are internal nodes. Okay. There's a special situation where one need not be an internal node. Be an internal node. So when you're looking at a formal definition of a tree, you need to start off somewhere. So a tree can be empty, or this is a multi-way tree. It can have some children, which are also trees. Trees. So going by this definition, you have this one is a tree. So 2, 3, 4 are also trees, and even 5 and 6 are trees because single node, and they are like the root node. But suppose there was only one node in the tree and that node was a root node, then it's something like that. So they are still trees. And we have also said even an empty node is a tree. Okay, so this completes the definition of what a tree is. And these relationships are, so basically, when we look at leaf nodes over here, and we said 5 and 6 are siblings. Similarly, we have 8, 9, 10, which are siblings. So what does it mean here? 5, 6, 8, 9, 10. If I look at this, these are nodes that have the same parent. The same parent. Okay. And now let us do some more definitions with respect to trees. A path in a tree. One moment. Okay, before we go to path length and so on. So how do we represent trees? Okay, so what we're talking about is, let's say you have any children tree, has many children. So we only have arrays and linked lists, which are available for us in a programming language. How do we represent the tree? It depends upon the application that we're looking at. The very beginning of the class, I talked about an application called Union Find. And for Union Find, the best representation is an array. And what we do is, it's like this. Let's say we have these, have an array which is indexed 1 through 10. And notice what I have done here. In the index 1, I've stored 0. In the index 2, I have stored 1. In the index 3, I've stored 1. 4, I've stored 1. Index 5, I stored 2. 6, 2. And 7, 3. And 8, I store 4. So it's like this. Actually, you're saying who are the parents of 8, 9, and 10? This is 4. Who are the parents of 5 and 6? This is 2. Who is the parent of 7? This is 3. And so on. And who are the parents of 2, 3, and 4? And you say this one's parent is 1. And who is the parent of 1? It's 0 because there is no other parent for that. It's the root of the tree. Okay, so this is one such representation that we can have. But this is not very general. Okay, this is not very generalized for many applications. It's very nice when you need to go from child to parent. You want to do things like set membership. Then this is a very nice data structure. Okay, for representing trees. The most common representation of trees uses what is called leftmost child right sibling representation. Okay, let us see what this is. What is the leftmost child right sibling representation? So if I look at the root here, its leftmost child is 4. Then 4's right sibling. Remember we said all elements at the same level which have the same parent are called siblings. So what we do is we say 1 points to 2, which points to 3, which points to 4. And now 2 points to 5, 5 points to 6, and we have 3 which points to 7, and this has no right sibling, and 4 points to 8, 8 points to 9, and 10. So what is nice about this? This is a linked list representation of trees. Sorry, a linked list representation of trees. So at every node, how many pointers do we require? See, because if I want to use, so this was nice for set membership, okay? And the good part was that it could take care of the array representation, can take care of any number of children. But it does not generalize when I want to go the other way around. For example, if I want to start from 1 and find out who are all its children, who are its grandchildren, it's a little more complicated. So what is done is a linked list representation seems more apt because it allows us many children, and at the same time, if you want to do a linked list, for example, you cannot do 1, 2, 3, 4, 5 because then you're forcing 5 links. If I can't allow that. So what we do is we start with only 2 links at every node. The root has no siblings. So at every node we have node. Notice that it has a pointer to a node at the same level and a pointer to its leftmost child. Node, there are 2 pointers. Okay. And of course, the problem is indirectly puts another hierarchy that you can reach the other siblings only through the oldest child. Okay. So now I'm going to give some definitions with respect to trees. What is a path? A path is a path from node A, node N1 to N2 is defined as a sequence of nodes N1, N2, Nk such that Ni is the parent of Ni plus 1, 1 less than or equal to I, less than k. The length of the path is the number of edges number of edges on the path, and in this example it will be k minus 1. Let's go back to this example. So let's say there is a path from node 1 to node 5. Length of the path is 1 and 2. So there are 2 edges going from 1 to 5. Okay. Okay. Now let us see what is the length of the path from here. You will not say this one has length of 2 because this is just a representation. The path is only 1 over here because it is still the direct child of 1. Okay, this is clear? Like as if there's a path over here. So we'll still call it a path of length 1. Okay, and path length is of course 0 from a node to itself. It's always nice to have, like the definition of 0, no? You have something for 0 path length because it's always easy to measure with respect to that. Depth of Ni is the length of the unique path, what is this, from root to Ni. Therefore, the depth of root, again here, is 0. And height of Ni is the length of the longest path from Ni to the leaf. Okay. Therefore, we can say all leaves, which are also trees, are at height 0. What is the height of the tree? Tree is the height of the root. Of the root. Of course, what are we going to take? We're going to take the height of the deepest leaf. Height of the deepest leaf. Let me tell you what I mean by this. For example, if I have a tree like this, one here, and I had 7, the height of the tree is 1, 2, and 3. Height of the deepest leaf. Okay. And this is also called the depth of a tree is equal to the height of a tree. And if there is a path from N1 to N2, then N1 is an ancestor. Otherwise, and N2 is a descendant. Then if N1 is not equal to N2, then N2 is a proper descendant and N1 is a proper ancestor. Okay. Then now, why are we so, we're defining parents, children, grandchildren, and so on and so forth. The whole objective is to perform what is called a traversal of trees. We'll take some examples afterwards, okay, of trees. Let me go back to this example of this tree over here. I'm going to draw a path and then tell you what are different ways in which you can traverse the tree and why are these important. Then we will study the binary tree in particular, which has very, very many applications. 7, 8, 9, and 10. Now, what I'm going to do is I'm going to, it's like, let's say this is a tree, and you just take a path, walk around the tree like this. Okay, I'm just going to take a walk around this tree. Okay, maybe I'll change the color. I'm going to just walk around the tree. Then we have 3 different traversals which describe what we saw with respect to the tree. Okay, these are the preorder, preorder, Inorder, and Postorder traversals. And these are extremely important, and we will see some special applications, especially when we look at binary trees. And what is preorder? In preorder, we output the node information, the first time we see it. First time we see it. Okay, on the path. The first time we see it on the path. And in Inorder, we output information about the node the second time we see it. See it on the path. In Postorder, we output the node the last time we see it on the path. That is, what I'm saying is, I have this purple path over here, and I'm going to take this purple path which goes around the tree. Notice that I'm not climbing any branches, or I'm not getting into. If you notice, I'm taking this purple path, not climbing any branches. I'm just going around the tree and I'm coming back. Okay, so now let's list what will be the preorder listing of this tree. 1, 2, 1, 1, 2, 5, 6, because I see this is the last time I'm going to see it. 1, 2, I'm sorry, this is the first time, 1, 2, 5. And I go around, then I'm seeing 6 again. Come back, then I see C3, 7, then I say 4, 8, 9, 10. So 1, 2, 5, 6, 3, 7, 4, 8, 9, and 10. What do I do in order? I said the second time I see it. So what am I going to do now? I will, I have second time, right? So I'm coming down. I'm seeing 1 for the first time. I see 5 here. I come back, and the second time, this path I saw first 5, go back. I saw 5 here. Then again, I'm seeing 5 here. I saw 2 in the onward path. This is the second time I'm seeing it. So I talk about 2 here. Then I see 6, and then this is the second time I'm seeing it. I list 6. Then I see 1. The second time I'm seeing it. Then I list it. Then I see 3, 7. 7, for example, first time, second time here. Then second time 3 here. Then I come down here, 8, 4, 9, and finally 10. Okay, so what do I have? This is a little bit complicated, but this is something that's done, not very much relevant in the context of a full tree, but we will see in the context of binary trees why this makes a lot of sense. 8, 4, 9, 10. And the post order listing is what will be the last time I am seeing the node. So this becomes 5, 6, 2, 7, 3, 8, 4, sorry, 8, 9, 4, sorry, 8, 9, sorry, I'm just making mistakes here. 8, 9, 10, 8, 9, 10, 4, and then finally 1. Okay, so this is your post order listing of the trees. So we'll stop here and continue with the next part.